Good morning, everyone. My name is Rita Nasr. I'm a PhD candidate at the University of Nevada, Reno. This is my third year at UNR, and I have been working on many projects, including the NCHRP 964, which is developing laboratory methods and specifications to test tag code materials, and which will be discussed in this presentation. Please note that this is an ongoing project with an expected completion date in spring 2023. Therefore, in this presentation, we will go through the project activities only. The overall performance of a pavement structure is significantly influenced by the characteristics of the tag code applied and the bonding quality of the tag code material used. Improper tag code application could lead to a 75% reduction in fatigue life, increase in rutting, shoving, and slippage. For this reason, a tag code should be selected based on its properties and characteristics and not on historical judgment. Knowing that a good bonding leads to a stronger pavement structure, this behavior can be jeopardized during construction when the tag is picked up by the tires or when durability problems exist. Therefore, in addition to bonding specifications, tracking and durability specifications should be considered as well when selecting the proper tag code. This research aims to produce a specification with related laboratory test methods for tag code material that allow prediction of their performance over a range of environments, pavement types, and construction methods, while considering tag code bonding, durability, and tracking behavior. The experimental plan includes sample preparation, interlayer shear testing, and finally a correlation between the ISS test results and the fundamental rheological properties of the tag code materials. 5 bottom layer surface types were considered in this research: the new AC, milled AC, HAC, as well as the new PCC and HPCC. The top layer was always new AC layer. HMA on HMA samples were prepared in the lab using gyratory compactor. The mixture types were 1/2 inch and 3/4 inch en masse mixtures, and 4 different binders were used to fabricate the mixtures. On the other hand, HMA on PCC substrates were fabricated in a large-scale test form referred to as the pave box. The pave box is approximately 11 feet square, constructed indoor with shoring on a solid slab and filled with several feet of subgrade and aggregate base. It is located at UNR inside of a building with a temperature control to allow for a successful curing process. Finally, 14 tag code materials were formulated and tested at Paragon and then shipped to UNR for ISS testing. Tag codes were applied at different residual application rates. As mentioned previously, tag code materials were formulated and tested at Paragon and then shipped to UNR. The first column summarizes the tag code material used in this research, the emulsions, and the hot applied binders tag code. Emulsions were recovered using 3 different recovery methods: the distillation, low temperature evaporation, and the vacuum recovery method. The second column represents the different types of the binders used in the mixture. The column on the right includes all the residue and binder performance tests adopted in this research. Moreover, asphalt performance testing was conducted on all materials, including the binders used in the mixture or as a tag code, as well as the residues recovered using the different recovery methods. This table is an example of a DSR output. The second one is an example of the parameters collected from the 4mm DSR test. And finally, the last table summarizes the takiness test results. All tests were conducted on original binders and for all residues obtained from each of the 3 recovery methods. However, the 4mm DSR was also performed on RTFOH binders and recovered residues. Moving to mixture performance, in particular to interlayer shear strength testing, samples were conditioned and tested at 25 C, low temperature 0 degrees C and 5 degrees C, or after moisture conditioning. Then a shear test was conducted to determine the interlayer shear strength according to HTTP 114 at a loading rate of 0.1 inch per minute, except for samples tested at low temperatures, where the loading rate was reduced from 0.1 inch per minute to 0.05 inch per minute in order to not exceed the fixture capacity. The laboratory HMA sample preparation consisted of a 3-inch thick bottom layer of asphalt mixture and a 2-inch thick asphalt mixture top layer with a tack coat at the interface. An air void of 7% plus or minus 1% was targeted. Milled surface samples were prepared by longitudinal grooving the surface using an angle grinder with a grooving disc, and aged surface samples were prepared by placing the bottom compacted samples in a forced draft oven at a temperature of 85 degrees C for 5 days, and then the surface was polished using a belt sander. Test specimen for bond strength testing of HMA on new and HPCC substrates were fabricated in the pave box. New PCC surface was simulated by tining the PCC surface with a PCC tining ray, whereas H surface was constructed by tining the PCC surface and then polishing the surface using a belt sander. After the top new AC layer compaction, the tining direction was marked to ensure that the shear direction was parallel to the tining direction. The weight of the tack coat applied was determined using the recommended residual application rate by NCHRP 940 project to control the amount of the residue left after curing for all the emulsions used. The paintbrush was used to apply emulsified asphalt, whereas a silicone brush was used for hot applied binder tack coat materials. Moreover, the tracking performance was evaluated using the BASF test. This test method was used to measure the time required for each emulsion material used in this research to set before opening to traffic. A 10-pound stainless steel wheel with quarter-inch wide grooves was rolled through 15 mil emulsions mat every 15 minutes into white cardstock until no further tracking was noted. Finally, the outcome of this research will focus on developing tack coat specifications in terms of bonding, tracking, and durability behavior of the tack coat material. Moreover, an NTPEP work plan, National Transportation Product Evaluation Plan, will be developed to define the procedures used to evaluate the properties of asphalt tack coat materials, in addition to a field work plan to validate the lab specifications developed in the field. Thank you everyone for listening, and please let us know if you have any questions.